Okay, not sure what I'm going to do with these boards after I say this. I'm either going to slide this that way or this way, and maybe refocus the camera so you can see everything. So we've established, at least intuitively, I hope, why the contribution of the path integral over curve 1 and curve 3 over path 1 and path 3. In other words, the integral over C3 plus the integral over C1 of your f dot dr. Number 1 depends only on how the function changes between here and here. In other words, how the function changes when you add delta y to a given coordinate down here. Okay? And that comes out just by the definition of the partial derivative with respect to y. And now we want to look at how the integral over path 2 and the integral over path 4 first of all depend on qx. Now again, the integral over path 2, okay, first of all, q is only integrated with respect to y. So p has no influence on the integral of q with respect to y, so we only have to look at the q function on this path and this path, where it's only y that's changing. X doesn't change on this path or this path, so p is irrelevant when we're on this part of the path, just as q was irrelevant when we're on the C1 or the C3. Okay, so again, p is irrelevant over path 2 or path 4. Just because we're integrating q with respect to y. Okay, a similar thing happens. Okay, the only thing that influences the difference in the value of the function on this path and the value of the function on this path is the x derivative of q. So only the x derivative of q matters between here and here. Only the x derivative of q drives a change from here to here in the value of the function. These paths having exactly the same length, then that's the only thing that makes a difference in the integral over path 2 and path 4. Now the paths are obviously in opposite directions, so you might wonder, well, if we do a completely analogous argument, intuitively we would expect that we'd have something very much like the negative py dA. So why is it positive? Okay, well, the why is because here we went from this path to this path. A positive py would imply a greater value up here. Of course, a negative py, a lesser value. But a positive py would give us a greater value up here than down here. Here, a positive qx would give us a greater value here than here. Because, of course, this is the direction of increasing x. But we're integrating from over this path before we integrate over this path, so that a positive qx would give us a greater value here than here, meaning that we'd have a lesser value here than we have here. So that's the reason for the positive qx. A positive qx is going to give us a greater value here than it is here. So when we subtract this from this, we're going to get a positive. It comes down to that. And it comes down to just, y is changing in the positive direction as we go from path 1 to path 3. But x is changing in the negative direction as we go from path 2 to path 4. For all those reasons, you have a different sign on this than you have on this. Okay, now we're actually running very short on time, so I'm not going to have time to do that whole development, but we'll do it next time. To verify Green's theorem, and then talk a little bit how we use this. We might run a couple of minutes over, but I can say this pretty quickly. Not sure I will say it pretty quickly, but I could, so maybe I will. Okay, let's just see how much board I've got to focus on here. Okay. And I said using Green's theorem, I'm going to start with verifying and there is more to Green's theorem than I've done on just a small rectangle. So I probably ought to talk briefly about extending small rectangles to large regions. So let's say we've got a curve C here, and we want to extend Green's theorem, which we know to be true, or at least approximately true, on small rectangles. And in the limit, when the miracle occurs, all differences disappear. Okay, so what do? Well, here's a typical small rectangle. The same thing is going to be true for any rectangle, and that's too small for me to label. So let me do some bigger small rectangles. Okay, so we have interior rectangles, like this one. And we're integrating around this rectangle in the positive direction. Now, this rectangle borders 4 different regions. It borders this region, where we're integrating in this direction, this direction, this direction, and this direction. You notice that the integral from here to here for this region is equal and opposite to the integral from here to here. So whatever happens between here and here is canceled by what happens between here and here in this region. And of course, we're adding the integrals over all regions. So when we add the integral over this region to the integral over this region, the contribution along this line, or this side of this rectangle, disappears. Well, the same thing happens when we integrate over this region. The contribution here disappears. And when we integrate over this region, remember we're always integrating in the counterclockwise direction. Then that takes care of the contribution over this part of the path. And then we integrate down here, and we integrate over this path, which again cancels what we have here. So the total contribution of this rectangle is subsumed by everything that happens on its boundaries. And the same thing is true almost on this region. On this region at the boundary, we're going to be integrating over this region. So we're going to have integrals like so. And that's going to cancel out anything that happens here. And then we have an integral over this region here that cancels what happens in adjacent regions. But we're left with the boundary where it doesn't cancel. And the same is true around the whole region. So by our cancellations, except on the boundary, theorem holds for all of C and D. Where D is the interior of the region. Okay. Well, that completes at least a sketch of the proof. You got to do it rigorously with epsilons and deltas to absolutely prove it, but the details are just the details. If you understand how to take limits and use epsilons and deltas, then it becomes very easy to prove the theorem. Okay, that's a sketch. You read it in your book. And I'm out of time, so as far as verifying and using Green's theorem, your book's going to show you how to do that. To verify it, you just do the integrals. Okay, and note this is very important. For conservative functions, both integrals are 0. Now, I'm not sure I totally specified it. These curves have to be closed, orientable. Okay? I think I said that. I could look back here and say, I didn't really say it. It's implicit because I used that little circle when I did the integral. And everything I've talked about is a closed region, so maybe a little flaw there in my presentation. Using Green's theorem, if you can't do one of the integrals, maybe you can do the other. In which case, you've done the one you can't do. Okay? The integrals are equivalent. And in many cases, you can actually get the formulas for some integrals that you can't otherwise get using Green's theorem. because a lot of times one of the integrals is easy to do just using integration technique, and the other is otherwise impossible. Okay? So, that's an introduction to Green's theorem. If you can do line integrals and area integrals, you can verify it. And if you can use Green's theorem to set up equivalent integrals, then hopefully you can do at least one of the integrals, so you know both. Okay, very, very powerful. Okay, hydrodynamics, electromagnetism, you can't do any of it without the big integral theorems that follow from Green's theorem and have a very similar feel to Green's theorem. Again, Green's theorem says what happens on the boundary determines what happens inside, and vice versa. There are even theories of cosmology that say that the universe is in some sense holographic, where the behavior of everything in, let's say, our four-dimensional space happens on a three-dimensional boundary of our four-dimensional space, is modeled. All the information in a higher dimension is there on a lower dimension. There are some really profound and incredibly neat things that follow if you just understand starting with Green's theorem and then extensions into three dimensions. And the extensions into higher dimensions are not as straightforward. You've got to use particle physics, string theory, whatever. And I talk about those things. I don't understand those things deeply. I'm not sure I even understand enough to totally appreciate how deep they are. So Ryan, that's your job, okay? And Richard, you do the same thing. You guys collaborate and prove all of cosmology and stuff like that, and then give me credit, okay? Okay, well, good. Richard, I'll talk to you just a little bit about registering for the course, and I'm going to turn off the camera.